Let us now talk about the clock, which is a periodic signal used to synchronize various operations that happen inside, for example, a microprocessor or a complex digital system in general. So complex digital circuits are generally designed for synchronous operation, that is, transitions in the various signals are synchronized with the clock. So that is the function of the clock. To take an example from real life, we have day and night, and that provides some synchronization to us. We all get up at about the same time, we go to the office, we work together as a team toward a certain output. Now imagine that we did not have day and night. Then we would all get up at various times, go to office at different times, and there would be no such thing as teamwork. And clearly that situation would be very chaotic and inefficient. And the clock serves a similar purpose in a complex digital system. It turns out that synchronous circuits are easier to design, much easier to design and troubleshoot, because the voltages at the nodes, both output nodes and the nodes which are internal to that digital system, can change only at specific times. That makes a big difference. Alright, let us now look at what a clock is. A clock is a periodic signal with a positive going transition and a negative going transition. So here is the clock. This is one period. The period is T. It has got a positive edge going from 0 to 1, and it has got a negative edge going from 1 to 0. And it is the clock frequency given by 1 over T which determines the overall speed of the circuit. For example, a processor that operates with a 1 gigahertz clock is 10 times faster than one that operates with a 100 megahertz clock. Here are some examples. The Intel 8286 processor, one of the early processors, which was used in IBM PC 80, had a clock rate of 6 megahertz, whereas today's computers, the PCs that we use, have CPUs which operate at 2 to 3 gigahertz. So that is 500 times faster than the IBM PC 80. So that is how dramatically things have changed. Let us now look at a clocked RS latch. So it has this additional clock input apart from S and R inputs, and it has got this block which is already familiar to us. It's reproduced over here. That is the NAND latch. And what we will do is call these inputs A and B, because S and R would be reserved for these inputs here in the clocked latch. Now in terms of these inputs, the operation of this latch is described over here. When A is 1, B is 0, Q is equal to 0. When A is 0, B is 1, Q is set to 1. When both are 1, then the latch holds its previous state. There is no change in Q or Q bar, and A equal to B equal to 0 is invalid, as we have seen earlier. Let us now look at the clock latch with clock equal to 0. If clock is 0, then A would be 1, B also would be 1, and that is irrespective of S and R. That means S and R are don't care conditions in this case. So that is what this is. Now if A and B are 1, then we are referring to this row here. That means Q and Q bar will continue with their previous values, like that. So that explains this first row over here. So as long as clock is 0, the latch outputs do not change. So for anything to happen, we must have clock equal to 1, as in these subsequent entries. When clock is 1, A is S bar and B is R bar. And knowing that, and knowing this table, we can now construct the rest of the entries in this table here. these 4 entries. Let us take R equal to 1. In that case, B would be R bar, that is 0. S equal to 0, A would be S bar or 1. So we have A equal to 1, B equal to 0. That is this row here. That means Q would be 0. And that is what we have over here. Let us take this row now. R is 0, so therefore B is 1. S is 1, therefore A is 0. So A is 0 and B is 1. That brings us to this row here, and that means Q would be 1, like that. What about R equal to S equal to 0? That means both A and B would be 1. That means Q would be the previous value of Q, like that. And when R and S are both 1, that means A and B would be 0, 0, and that condition is invalid. Here is the summary. When clock is inactive, that is 0, A and B are both equal to 1 and the latch holds the previous state, this entry here. When clock is active or 1, then A is S bar, B is R bar, and using the truth table for the NAND RS latch on the right hand side, this table, we can now construct the truth table for the clocked RS latch, this one. And let us remember that the above table is sensitive to the level of the clock, whether the clock is at level 0 or at level 1. Later we will see flip-flops which are sensitive to transitions in the level, either from 0 to 1 or 1 to 0. Let us now try to understand these waveforms for the clocked RS latch using this table here, which we looked at in the last slide. So here is the clock waveform, periodic. Here is the R input given to us, and here is the S input. And let us assume that the latch starts in a state Q equal to 0. So at T equal to 0, we have Q equal to 0. Now, as a result of these inputs and the clock waveform, let us see what Q should be. Point number 1, nothing would happen when clock is 0. So up to this point, nothing is expected to happen, because when clock is 0, Q just continues with its previous value. So that happens up to here. Alright, now in this interval, clock is equal to 1 and R is 1, S is 0. So we look up this entry now. R is 1, S is 0, and Q is shown here as 0. So Q will continue to be 0 in this interval. Now we have clock equal to 0, so nothing is expected to happen. We don't even need to look at R and S. So we draw this Q equal to 0 part here. Now the clock has become 1 there. R is 0, S is 1. R is 0, S is 1. So Q has become 1, and that is why we have shown this transition here. Once again, clock has become 0 there, and therefore this will continue. At this point, clock turns 1 again. We have R equal to 1, S equal to 0, Q becomes equal to 0. So we have a transition now from 1 to 0. Now clock is 0 in this interval, so Q cannot change. And in the last interval here, clock is 1, R is 0, S is 0. R is 0, S is 0. So that means Q would be its previous value. So Q will continue to be 0. And that is our complete Q waveform. Let us now talk about edge-triggered flip-flops, which are very commonly used. The clocked RS latch, which we have seen earlier, is level sensitive, as we remarked earlier as well. That means its operation is sensitive to the level of the clock, whether the clock is 0 or 1. If the clock is active, clock equal to 1, the flip-flop output is allowed to change depending on the R and S inputs. If clock is 0, then Q cannot change. It continues with its earlier value. On the other hand, in an edge sensitive flip-flop, the output can change only at the active clock edge. So level equal to 0 or level equal to 1 is not sufficient. What is required is an edge, that is clock transition from either 0 to 1 or from 1 to 0. And here are the symbols for edge triggered flip-flops or edge sensitive flip-flops. Here is a positive edge triggered flip-flop. That means it is triggered by a positive edge in the clock. What is a positive edge? It goes from 0 to 1. This is the symbol for a negative edge triggered flip-flop. It is triggered by a negative edge in the clock, which goes from 1 to 0, like that. Alright. Now the common feature of these symbols is this triangle. That triangle indicates that it's an edge triggered flip-flop. And whether it is a positive edge triggered flip-flop or a negative edge triggered flip-flop is indicated by this circle here. If we have a circle here, then that's a negative edge triggered flip-flop, and absence of the circle indicates that it is a positive edge triggered flip-flop. So from this symbol we should be able to make out whether it's an edge triggered flip-flop, and if so, whether it is a positive or negative edge triggered flip-flop.